Yeah, what a pleasure to be here to talk about helical anchors. As Christoph mentioned, this is part of a bigger scope within the helical anchor theme. We have been working with Win and University of Dundee, all things related to helical anchors. And as part of the scope, there's also helical anchor groups and a concept of helically embedded plate anchors that will be presented tomorrow in one of the sections. But today I'm going to be talking about the jetted helical anchors. And just to start, what is a helical anchor? For everybody, probably you know, but it's a helix that is connected to a shaft. And this is installed by applying a torque and a thrust force at the top, pretty much as a screw that everybody knows. It can have one or multiple helixes and all different shapes. And why do you think this is a good solution for anchors? Because it's a silent and fast installation compared to traditional anchors. It has the potential of having high capacity to its own weight because of the plate. There's a lot of bearing area down there. It's also lower manufacturing cost because it can be as simple as welding a plate to a shaft that could be mass-produced and standardized as well. And there's also claimed to be easy to decommission. You can reverse the torque and remove it from the soil, pretty much as you do when you're putting away your furniture. You just remove the screws and off you go. It's important to mention that this is common practice onshore, so it's not new technology. And also for small offshore applications, as Christoph showed on his presentation, mussel farms and other fisheries, they already use this offshore. But also large piles onshore, retaining anchors for retaining walls and rectification of existing structures. But the problem offshore is that the size is much bigger, the loads are bigger, so the anchors need to be much bigger, which brings a lot of shortcomings. The first one being the large installation torque and thrust force required to install such large anchors. They are also not very good for lateral loads because they have a relatively thin shaft compared to a conventional pile. There's also not high torque installation rig available at the moment. There are some prototypes like from the Herema at the bottom, but they use very large vessels for very large piles. And there's also lack of confidence in the solution overall because of the limited use so far. That's where the jetted helical anchor comes in. We use these as a mitigation for the large installation torque, and also which can provide an installation with a smaller vessel or a smaller rig because of the reduced torque as well. So we're aiming to tackle those two limitations with this solution. So we did a bunch of tests in our centrifuge. So here's just a little bit of the setup, how it looks like. So it's a torque and axial load cell, which is connected to a rotary fluid union. And this is connected to the helical anchor, or the screw pile. So as you can see on the image here, this chamber has rollers. So the chamber is free to rotate compared to the shaft that is moving in. And we have the hose connected to this chamber that pumps the fluid in, that goes through the over hose down to a hollow shaft, and then exits at the bottom through jets around the helix. And then we tested some different configurations to see what would work and what would not, and always comparing results with a non-jetted reference test. So let's look at some results. First, a video of how this works in the centrifuge. So we start, everything is done in flight, so we don't need to stop the centrifuge at any point. We do a first installation without jetting to avoid scouring all the soil near the surface. Then we turn on the pump, we start jetting, and the anchor goes in by its own self-weight, or a constant weight that we apply to the anchor. We wait there at the final position for pore pressures to dissipate, and then we conduct the extraction, everything while measuring torque and axial force on the load cell above. And then we conducted several tests with different jetting flow rates, and I'm going to show some of the results here. So let's talk about the installation torque first. In this plot, you can see it's a model torque against installation depth. And those two curves are the reference tests, which are non-jetted conventional helical anchors. The difference between the two is just the constant weight that we assign to the anchor, one being 15, the other one 50 newtons. And we can see that there's not a huge difference between those, and the anchor just pulls itself in. So there's no need to apply a very large thrust force at the head of the pile. And then we started jetting with different flow rates, starting from small, 0.5 milliliters per second in model scale. Then we went to 1, and then 2 milliliters per second. And what we found is that actually we found a steady state torque with depth, which means that the torque was not increasing anymore as the pile penetrated, which was quite interesting and to be honest, not expected at that point. And then we tried different configurations. So we took the green curve there, and then we started changing the jet configurations. So we can see that if we only jet through the conical tip, not much help on the torque. But if we jet around the helix at the tip, it gets a little bit better. And the best outcome was at the top, at bottom of the helix, which makes sense, which is where most of the surface area is and most of the torque. So that was the overall best configuration. So let's put all together in a torque plot. So this is the installation torque divided by the reference torque for the non-jetted anchor against the flow rate. And what we can see is that for the same depth of installation, the torque reduced about 70%, even for those relatively small prototype flow rates. And what we think is that the flow rate is only enough to generate some pore pressure and reduce the effective stresses around the helix, but is not big enough to actually fluidize the whole soil and scour the soil to the surface. But every time I talk about this, people ask me, okay, but what about the capacity? That's the big question, eh? So I'm not gonna lie, capacity does reduce if you install the anchor to the same depth, about 40%. But then when we look at the capacity to torque ratio, which is how much capacity you can get for a unit of torque, actually jetting nearly doubled this value if you go to the same depth, which is quite interesting. Okay, so we saw jetting reduces torque, that's clear. But if the torque is less for a given rig that you have in the field that has a torque capacity, you can probably go much deeper if you're jetting. So what happens to the capacity in this scenario? So remember that steady state torque. So it turns out that there's 10 kilonewton meters in prototype scale. So we did non-jetted installations targeting this torque, which stopped when this torque was reached. And this was about 1.6 diameters for the non-jetted anchor. And this is the capacity that resulted. Then we did the same for a jetted installation, so targeting also the same torque. And then this is the capacity that was observed. So 13 times more capacity for the same installation torque, which was quite good. Now we can do a simple calculation, try to put this into perspective for a larger installation rig. So for the anchors that we did, this turns out to be a 3.6 tons per kilonewton meter, the torque to capacity to torque ratio. So if we assume that there's a rig in the field, which we hear about 500 kilonewton meters is what is available offshore currently, that would result in a 18 meganewton anchor, which is not bad. There's a lot of potential there, especially considering that this was just a pilot study that we did. And I have to mention here that actually the anchors, they could have gone deeper. We didn't see the torque increasing yet. We had to stop due to physical limitations because, to be very honest, we didn't expect this to be so successful at the first trial, and our models were not long enough. So there you go. There's already potential for new work, trying to see what's the biggest or what's the biggest capacity we can get. So try to summarize this. In terms of torque, I think it was pretty clear. The jetted installation reduced the torque significantly. And although the capacity also reduces, because the torque reduces more significantly, you can install those anchors deeper with a similar torque, which significantly increases the capacity. And this brings a lot of applicabilities for this solution, such as if you can install the same anchor much deeper, as I showed in those tests, but you may also use a smaller vessel to do the installation of those anchors, which it's also ends up in savings overall. Or you can choose to install a larger anchor or with a small vessel, depending on the application and the necessity of the projects. So overall, we think this is a promising solution, and we look forward to explore this a little bit more in the future. And thank you all for the attention.